Hello, this video is about how to write proofs by induction about divisibility. So please have a bit of paper and a pen so you can pause as you go through and do the working for yourself. So, if you take 10 to the 1 minus 3 to the 1, it's 7, which is obviously divisible by 7. If you take 10 to the 2 minus 3 to the 2, 10 squared minus 3 squared, it's 100 minus 9, which is 91, which is divisible by 7. If you take 10 cubed minus 3 cubed, it's 1000 minus 27, which is 973, and that's divisible by 7 too. Maybe it's a general rule. So you can try to prove it's a general rule by proof by induction. So in this, our claim will be that 7 divides exactly into 10 to the n minus 3 to the n for all n. This line means divides into. Notice we write it 7 divides into 10 to the n minus 3 to the n. It's not, you don't put the line afterwards because the line doesn't mean divisible by, it means divides into. Okay, proof by induction. What is step 1? Proof by induction. Step 1 is to prove that the claim is true for n equals 1. Okay, n equals 1. Does 7 divide into 10 to the 1 minus 3 to the 1, which is 10 minus 3? Obviously it does. Step 1, all done. Okay, do you remember how we start step 2? Yeah, step 2 is to prove that the claim is true for n equals k plus 1 if it is true for n equals k. When we start step 2, we don't know that the claim is true for any k except k equals 1. If we'd done step 2 before step 1, which we can do, we wouldn't even know it was true for k plus 1 equals 1. But if we have step 1 and step 2, then we know it's true for 1. Step 2 will then tell us it's true for 2. Step 2 will tell us if it's true for 2, then it's true for 3. If it's true for 3, then it's true for 4. If it's true for 4, then it's true for 5, for 6, and 7, 8, and for all numbers. In step 2, we want to prove. The thing we want to prove is that 7 divides 10 to the k plus 1 minus 3 to the k plus 1. That's the thing we want to prove, and what we're starting off from is I suppose, for the sake of argument, that 7 divides into 10 to the k minus 3 to the k. This claim is true when we plug k in instead of n. Okay, we want to find out something about 10 to the k plus 1 minus 3 to the k plus 1. And we know this is the assumption that we can use. So let's get this to have something like this, something looking like that in it. Well, the first thing we can do is take it down to kth powers. Okay, that looks a bit more right. However, we've got 10 to the k here, and that's 10 to the k minus 3 to the k here. And what we can do now is a bit like completing the square. We'll make this a complete 10 to the k minus 3 to the k. And now, I've replaced that by that, which means I've taken away this 10 3 to the k's. But if I add them back in, same sort of thing as you do with completing the square, then I'm still right. And of course, the minus 3 times 3 to the k is still there. Okay, that looks a bit better, because what we can do now is take away the 3 to the k from the 10 3 to the k, so we get 7 times 3 to the k. Okay, but 7 divides 10 to the k minus 3 to the k, which is what we've assumed here, and 7 divides 7 times 3 to the, 7 times 3 to the k, obviously. Therefore, 7 divides 10 to the k plus 1 minus 3 to the k plus 1, which is exactly what we wanted to prove. So we can write our Halmos stop. We have finished step 2. We have to do one more thing to complete the proof. Do you remember what the last thing we have to do is? We have to write at the end we write, therefore, true for all n by induction. What that's telling the reader is we're putting together step 1 and step 2. Step 1 by itself doesn't prove a lot. Step 2 by itself doesn't prove a lot. Together, the two steps prove everything.